Okay, in an earlier video we introduced the idea of partial differentiation. So if you've got a function with multiple variables in, you differentiate with respect to one variable at a time and keep all the other variables as constants. So if we differentiate this expression here with respect to x, then we treat the y bit as constant, so x squared becomes 2x, so we've got 10x from differentiating this part, and then the y squared bit doesn't change, it's just a constant. Similarly, if we do dz by dy, then the y squared bit differentiates to 2y, so we get 10x squared. So the x squared this time is not changing, that's a constant, and y. Now what we could do is we could go one step further, we could differentiate again. Okay, so just like with ordinary derivatives, how we can find second derivatives, third derivatives, and so on, we could do the same with partial derivatives. So let's try that. So if we wanted to, so if we took the first equation there and differentiated it again, okay, so we're going to do d by dx again on this one, then we'd write that as d2z by dx squared. So just differentiate this again with respect to x, and we just get 10y squared. And we could do the same with the other one, and we'd get 10x squared. But then what we could also do, which is different now, is we could differentiate first with respect to one of the variables, and then the second time with respect to one of the other variables. So let's go back to this, okay, and then differentiate this expression now with respect to y. So if we differentiate this with respect to y, the 2 now comes down, so I end up with 20x times y. And if I did the same sort of thing here, so I took this expression, dz by dy, now differentiated with respect to x, then I get 20xy. And what you notice is that we've got the same answer. Okay, so 20xy in both cases. Now, how do we write this a little bit more clearly? Well, so this one here, d by dy times dz by dx, we would write as dz by dy dx. So when we write it like this, it means we differentiate with respect to x first and then y. So we read it from right to left. Now the problem is that there's another common notation which is used, and it's this subscript notation. So we could also write this as z with the subscript xy, and that's meant to mean that we differentiate with respect to x first then y. So in this notation we read from left to right, so this first, differentiate to this first then this, and in curly d notation we differentiate with respect to this first then this. It's just something that we have to deal with. Okay, it's a bit unfortunate. Right. Now we find that this is always true. The second derivatives, the order of those derivatives doesn't matter. Okay, so generally we can write down that zxy equals zyx. Okay, or dz by dy by dx. Oops, sorry, I should have a 2 in there as well. Is equal to d2z by dx dy. So they're the same. Now we can exploit that if we've got a function which is quite complicated in one of the variables but quite simple in one of the other ones. So for example, let's say I had z equals 2x cubed y plus the square root of y times sine of 5y. And then let's say I wanted to find this. So this, In other words, I want to differentiate with respect to y and then with respect to x. Now, if we differentiate this with respect to y first, the first term would be quite easy, that would just be 2x cubed. But here, we've got a product, we'd have to use the product rule, and then chain rule again for the sin 5y bit. It's going to just take a little bit of time. If this was more complicated, then it would be even worse. But what we could say is, well, if we want to find zyx, well, that's just the same as finding zxy. So we differentiate it with respect to x first and then y, and it should give us the same answer. Now, if we differentiate with respect to x first here, then what happens is the second term will just be equal to 0, because if we're differentiating with respect to x, then this term is just a constant, and constants always differentiate to 0. So we find that dz by dx is equal to differentiate this part with respect to x, so the 3 comes down, so we've got 6x squared times y, and this bit, as I said, just differentiates to 0. So then if we do this differentiate now with respect to y as well, so we've got dz by d2z by dy by dx. Okay, so if we've got this now, then we just need to differentiate just this expression with respect to y, and y differentiates to 1, so we just get 6x squared. And that's it, simple. So this is the second derivative theorem, and it can make our lives a lot simpler.